Hey everyone, Praveen this side. I hope you guys are doing great. And if you're not, keep hustling because one day you will definitely reach the height of greatness. So today we are going to solve the problem maximum product subarray, which is very similar to the problem that we solved yesterday. That is Kadane's algorithm. And the difficulty is medium. So let's read the description first. The description says given an array ARR that contains both positive and negative integers may contain 0 as well. Find the maximum product that we can get in a subarray of ARR. So we have been given an array which contains both positive and negative integers, right? And which also may contain 0. Now we need to find the maximum product subarray of array. There's a note point here that it is guaranteed that the output fits in 32-bit integer. That is, our product will never overflow the 32-bit integer. So the problem description is clear. Now let's get into examples. So in the example 1, the array is -2, 6, -3, -10, 0, 2 and the output is 180. The explanation here says the subarray with maximum product is 6, -3, -10. That is this subarray, right? And the product of this subarray is 6 into -3 into -10, which results in 180. And in the second example, the array is -1, -3, -10, 0, 60. So the output is 60. The explanation says the subarray with maximum product is 60. So an individual element in an array can also be considered as subarray, right? And finally, in the third example, the array is 2, 3, 4 and the output is 24. Here, the explanation says for an array with all positive elements, the result is product of all elements. That is, since all the elements in this array is positive, so we can take the product of all the elements, which results to 24. So we have understood all the examples very well. Now let's take the example 2 as reference and try to find few observations from it. Because example 2 has a lot of observations to be observed. So we need to find the maximum product subarray, right? So what does the brute force approach says? Firstly, generate all the subarrays. Now to generate all the subarrays, first we'll fix our pointer here. So one of the subarray is this. Now when we try to expand this subarray, so the next subarray will be this. Then the next subarray will be this. Then this. And finally this. So by fixating the point here, we have generated this, and this, right? Similarly, when we fix a point here, the subarray will be this, and finally this. So this way we'll generate all the subarrays. And while generating the subarray, we'll keep the track of current product, that what is our current product, right? Which will be initialized with 1. And in parallelly, we'll also update our maximum product subarray. So let's see the pseudocode first. So this is the brute force approach for generating all the subarrays and finding the maximum subarray product, right? So firstly, I have taken max product to be negative infinity so that we can maximum it as maximum as possible, right? And here we are running 2 for loops. One for loop is to fixate the point that we were fixating here, right? And inside we have initialized the current product to 1. And in every iteration we are multiplying array of j with the current prod, right? And after we update our current prod, maybe this could be the potential maximum prod, right? So we are updating our maximum prod with the previous maximum prod and the newly generated current prod. Now after we generate both of the for loops, our max prod will have the maximum product of the subarray, right? So we'll return it. So this is the brute force approach. Now, what will be the time complexity for this approach? Since we are running 2 for loops, so the time complexity becomes O of n square. And the space complexity will be O of 1, since we are just using 2 variables, max prod and current prod. So I want you guys to convert this pseudocode into normal code and run it. Because brute force is an underrated skill. Until you don't code in brute force, how can you optimize it, right? It's not like you can directly write the optimized code. First you will run the brute force code. Then you might find some issues with the brute force code. Then only you will optimize it, right? Now, will this code work for our given constraints? No, because our given constraint for n is 10 to the power of 5. So our n square becomes 10 to the power of 5 into 10 to the power of 5, which becomes 10 to the power of 10. But our compiler can only execute 10 to the power of 8 instructions per second. Now let's see how we can optimize the time complexity. Now before optimizing our code, there is a prerequisite that we are going to follow, that is Kadane's algorithm. So if you know Kadan's algorithm, where we were solving the maximum sum subarray, right? And here we need to find the maximum product subarray, right? So we can't use Kadan's algorithm, right? But we can use the logic of Kadan's algorithm and modify it in our way so that we can find maximum product subarray, right? So please watch Kadan's algorithm. I will provide the link to this video in the description. By watching this video, you will get the intuition like why we need to use Kadance algorithm to find the maximum sum subarray, and the same logic we'll be using to find the maximum product subarray, right? And if you already know Kadance algorithm, then great. So let's use the Kadance algorithm to find the maximum product subarray. So similar to Kadance algorithm, we have taken two variables, current product and maximum product. In Kadance algorithm, we take current sum and maximum sum. So let's start the execution from index 0. So at index 0, the element is minus 1. So we'll multiply 1 with minus 1. Then this number becomes minus 1, right? And we'll check whether current prod is greater than max prod. Yes, since it is greater, so we'll update our max prod to minus 1. Okay. Now we'll move to index 1. At index 1, the element is minus 3. So we'll multiply minus 1 with minus 3, which results in 3. So we'll update our current prod to 3 and check whether 3 is greater than minus 1. Yes. So we'll update our maximum prod to be 3. Now at index 2, the element is minus 10. So we'll multiply 3 with minus 10, which results in minus 30. So our current prod becomes minus 30. And we'll check whether minus 30 is greater than 3. No. So we'll not update our maximum product. Now at index 3, the element is 0. So what we used to do in Kadance algorithm when the element is 0? We used to set the current sum to 0. But here we are using the current prod. So we'll reset it to 1. So the current prod here becomes 1. Okay. Now if you didn't understand what did I just say here, you probably haven't watched Kadance algorithm. So please watch Kadance algorithm. Now here we have reset the current prod to 1, right? Now at index 4, the element is 6. So we'll multiply 1 with 6, which results in 6. So we'll update our current prod to be 6. And we'll check whether 6 is greater than 3. Yes. So we'll update our maximum prod to be 6. And here our execution got completed. So our maximum prod is 6. But if you look carefully, is 6 is the maximum product? No. Because if we consider this subarray, then the product is minus 3 into minus 10, which results in 30. So technically our answer should have been 30, but why did we get 6? It is because we have initially multiplied minus 1 here, right? If we didn't have this minus 1, then for this subarray, the product have been 30. And we needed to multiply minus 1 here because we were moving forwards, right? Now, how to overcome this? It's simple. How we have traversed from start to end, right? Again, we'll traverse from end to start. Now, what advantage will we get by traversing from end to start? When we traverse from end to start, right, the subarray we consider will be just this and we'll discard this element, right? So, this is the observation that we found. Now, let me reset this board and we'll dry run from end to start. Here, I have reset the current prod to be 1 and maximum prod I didn't reset because this could be the potential maximum product, right? Now, we'll start from index number 4. At index number 4, the element is 6. So we'll multiply 1 into 6, which gives us 6. So the current prod becomes 6. Now we'll check, is 6 greater than 6? No. So we'll move to index number 3. At index number 3, the element is 0. So we'll reset current prod to 1. And we'll move to index 2. At index 2, the element is minus 10. So 1 into minus 10 will result in minus 10. So we'll update 1 to minus 10, right? And check whether minus 10 is greater than 6. No. So we'll not update our max prod. Now at index 1, the element is minus 3. So we'll multiply minus 10 into minus 3, which results in 30. So we'll update our max prod to 30. Right. And we'll check whether 30 is greater than 6. Yes. Now since 30 is greater than 6, we'll update our max prod to 30. So in this way, we have achieved this subarray, right? And finally, at index 0, the element is minus 1. So we'll multiply 30 into minus 1, which results in minus 30. So we'll update 30 to minus 30 and check whether minus 30 is greater than 30. No. So we'll not update the maximum prod. Now, when we traverse both left and right, whatever max product we got is the final maximum product that we can return. So that's why I have used example 2 from the problem example, so that it was giving us the full observations. So because of example 2, we got the idea like why not only to traverse frontwards, we should also traverse backwards, right? And we have slightly modified Kadane's algorithm here. Now, since we understood the observation, let's get into the code. So here's the code in C++, although the logic remains same. So the function name is maxFraud and array is passed as parameter and we need to return the maximum product, right? So firstly, I have taken the array size and I have declared two variables, maximum prod and current prod. Max prod to be int main and current prod to be 1. Now here I am running the forward loop, that is from 0 to n minus 1. And in every iteration, I am multiplying current prod with the array element and updating the max prod. And parallelly updating the max prod by the maximum of previous max prod and the current prod. And at any point, if we are getting the current prod to be 0, we are updating current prod to 1. So this was the forward iteration. Now here we are resetting the current prod to be 1 and we are ready to do the backwards iteration, that is from n minus 1 till 0, right? And inside we are doing the same stuff, that is multiplying array of I with the current prod and finding the maximum prod to be max of previous current prod and current prod. And if at any point our current prod becomes 0, we are updating our current prod to be 1. So this is the backwards iteration that we were doing, right? And after doing both forwards and backward direction, whatever max product we generate, will simply return it. So the code was simple, right? But the observation of using Kadane's algorithm and modifying it and traversing both forwards and backwards is the main learning that we learned in this video. Now, what will be the time complexity for this approach? Here we are running two for loops, both for forwards and backwards, which becomes O of 2n, which can also be written as O of n since 2 is constant, right? So the time complexity becomes O of n. And what is the space complexity? Here we are just using variables and not considering any extra data structure. So the time complexity will be O of 1. So I hope you guys like this video. If you guys really did, then please like, share and subscribe. If you have any doubt at any point, please post in comment section. I'll try to respond it as quickly as possible. And if you have any feedback in my teaching, please comment it down too so that I can improve in that portion. So meet you guys in tomorrow's video. Till then, stay safe, stay happy and peace.